Greetings and welcome, friends. Welcome to a brand new chapter, a brand new world to explore. Today, we are starting chapter 5, which is talking about systems of equations. Okay, so far, up to this point, we've represented an equation or a function as an algebraic set of numbers and variables and equal signs and operations as an equation, right? We've represented them as a table of values, as a list of inputs and outputs. We've represented them graphically on a coordinate plane. And now, it's like I'm teaching you to juggle almost. Like you guys have been like, all right, wow, I can like throw this equation up and catch it. And now I'm like, now do it with 2 at the same time, right? Which is a system of linear equations. So a system of linear equations is a set of 2 or more. Wow. So you could have multiple equations going on simultaneously. Linear equations in the same variables. An example is shown below. So if I have a system, sometimes you'll see a curly brace around both or all equations at play. And the system is basically saying, all right, here's multiple equations. We could put these in y equals mx plus b if we wanted. We could represent them different ways. And my question is not just what are the solutions of this equation, right? Because you might have 1 plus 6 is 7, 2 plus 5 is 7, right? You'd have multiple combinations. 0 plus 7 is 7. You'd have multiple solutions of that particular equation, and we actually know that that represents a line on which there are infinitely many points that make this equation true. Infinitely many combinations of x and y that if I plugged in here would make this equation true. But now I also have this equation, which in and of itself has infinitely many combinations of x and y that make it true. And when I have a system, I'm looking for the points, or maybe there is no point, that makes both of the equations true at exactly the same time. And so a solution of a system of linear equations in 2 variables is an ordered pair, right? So that's our x comma y. That is a solution of each equation in the system. Like I pointed out, there are infinitely many solutions to this, infinitely many to that, but there is only one holy grail of all the points that will make both of them true at the same time. Okay, so let's do example 1 together. Mi con mis amigos. It says, tell whether the ordered pair is a solution of the system of linear equations. So here I've got an ordered pair, so that's like our xy ordered pair, and I've got 2 equations. Hey, actually, these were the same equations from earlier, guys. The same ones. And if I want to check whether it's a solution of the system, I've got to check it in both of those equations. So I'll work with 2 different colors here. So let's plug it in for the first equation. So 2 plus 5, is that equal to 7? 7 equals 7. Check it. That's true. True. So this point works in the first equation. But like I said, there are infinitely many points that work in that equation. So let's not get too excited yet. We don't know that it's a solution of the system, the combined set of equations, until we also know that it works in the second equation. So let's see, what's 2 times 2 minus 3 times 5? Is that equal to negative 11? So now I'm plugging this point into the second equation for x and y. So let's see, 2 times 2 is 4, minus 3 times 5, so that's going to be minus 15. The question is that equal to negative 11? And voila, negative 11 equals negative 11 is a true statement if I ever saw one. Cha-ching. Therefore, I could say 2 comma 5 is a solution. All right, so it's not just a solution of any one line, it's a solution of both lines at the same time, which graphically speaking would be when those 2 lines intersect one another. All right, so it's got to work in both. Let's do a quick check on this one. All right, quick. So here's my x, here's my y. Let's plug it in to the first equation. So when it is 0 equal to -2 times -2 minus 4, right? So I'm just plugging in the y, plugging in the x, and then I'm PEMDASing it. I'm not using algebra, so I'm not like adding 4 to both sides or things like that. I'm just order of operations. 0 equals -2 times -2 is positive 4, and 4 minus 4, oh, 0 equals 0. Man, that is so true. Wow, so true, guys. Man, one time, like, my friend shot me a text. He's like, hey, 0 equals 0. I'm like, man, that's so true. Ah, classic, right? So true. Let's plug it in to see if it works in the second equation, though. Don't get too excited. It might not be a solution of the system. It just might be true for this first equation. So let's see, 0 equals -2 plus 4. So I've plugged in the -2 in the x slot. I guess I don't really need parentheses because it's not being multiplied by anything. So let's see, is 0 equal to -2 plus 4 is positive 2? Oh, no, you didn't. No, it's false. Oh, guys, so sad. Sorry, -2, 0. You worked for one of our equations, but you are not a solution of the system. All right, so not a solution of the system. But now, our question would be, all right, so here's a way to determine whether or not a point is a solution of the system. But here's the question, how could I find the solution? Is there a point that makes both of those equations true at the same time? How would I find that point? How could I discover the one thing that's going to make everybody happy when it comes to those equations? And that's going to be the theme of really this entire chapter of how do I find solutions to systems? Okay, how do I find a point that makes multiple equations true all at the same time? And today, the technique I'm going to show you is solving by graphing. All right, which I know, to be honest, graphing, not my favorite. It works okay when solving these things, but it's not as accurate as some of the future solutions or means of solving that I'll show you. So let's see, solving a system of linear equations by graphing. Okay, so step 1, graph each equation in the same coordinate plane. I can do that. Estimate, here's its weakness. It's an estimate, okay? It's not going to be super close. Sometimes we'll get it right, but it won't be exact most of the time because our accuracy when graphing is limited. And then it says, and then step 3, check the point from step 2 by substituting for x and y in each equation. It's got to work for both of them of the original system. All right, so let's go on this adventure together, friends. Example 2, you've already got this written down. You guys are so fast. How do you write it so fast? I don't understand. I didn't even put it on the screen yet. Here we go. Example 2, we're going to graph both of these lines on the same coordinate plane. So that means I done need myself a coordinate plane. Let me get one for myself. I think you already have one. I set you up for success. Here we go. All right, so let's graph these on the same coordinate plane. To graph these, hey, what form are these lines in? What form is that in? Is that in standard form, slope-intercept form, point-slope form? Slope-intercept form. So let's use slope-intercept form. So m equals -2 for this line, m equals 4 for that line. My y-intercept is 5 for the first line, b equals 5. My y-intercept is -1 for the second line. And let's just like plot these points. Let's graph them. So let's graph the first line. Tell you what, I'll graph the first line will be blue. The second line will be this fuchsia purple color. All right. And now our goal is we'll graph them both on the same plane and then attempt to find their intersection. Okay. So yeah, you can grab a ruler. Great idea. Good idea. Yep. Es un buen idea. So let's graph using slope-intercept form. You guys are masters at this. So let's see. Up 5 for the first one. 1, 2, 3, 4, 5. Plot that point. B. Yep. And the slope is -2. So down 2 and over 1 and down 2 and over 1. Down 2 and over 1. And let me draw a wonderful sky blue, aqua, marine, teal line passing through those points. And deraw that line. There we go. Lovely, lovely blue line. All right, let's graph the other equation, right? And you guys, like I said, you're masters at graphing. So let's see. Y-intercept was -1, right? All of our skills are coming back to us now. Slope is 4. Wow, so that's up 4 and over 1. Up 4 and over 1. Up 4 and over 1. Yikes, it's getting a little messy over there on my grid, but that's okay. That's what happens when you graph multiple lines on the same coordinate plane. Looks like something about there. All right, so there's my 2 lines. Now, the question is, what is the intersection of these 2 lines? All right, they do in fact intersect. The purple line has infinitely many points on it that make it true. The blue line has infinitely many points that make it true. But where is the one point in which, like, they're both going to be able to live in harmony and peace and agreement with one another? Where are they both true? Yeah, it looks like 1, 3. So that's our suspected solution. All right, our suspected solution. We're going to do a quick check with it, though. So let's check it with the blue. Check it. So let's see. Is 3 equal to -2 times 1 plus 5? So is 3 equal to -2 plus 5? 3 equals 3. It works. Now, if it didn't work, remember our solution for some of these are going to be estimates. All right, so my check should be close then. If it was an estimate, if I was off, like what if I said like 0.9 and 3.1 or something like that? My check, these would have been close to each other, but not exact. And that would have been tolerable for us, depending on kind of how accurate we were able to get with our graph. So let's check the point in the other one. So let's see, plugging it in this equation, I would have 3, is 3 equal to 4 times 1 minus 1? Oh, I got a feeling. Ooh. Yeah, I think we found the solution, friends. Cha-ching. Beautiful. So that means 1, 3 is the solution. It checked out for both of these equations at the same time. And we found it all on our own. Isn't this wonderful? It's lovely. Lovely, really lovely. Let's see. Let's do one more like this. I'm going to do monitoring progress question 4. All right. I want to do at least a couple of these, but we don't have all the time in the world. Not all the world's problems can be solved in a day, friends. Let's see. So I'm going to do question 4. It's got some fractions for us. I figure you guys are afraid of fractions. They're the one horror that continues after Halloween. But that's okay. Don't be afraid. It's gonna be okay. Gonna be okay, my friends. All right, so here we go. All right, let's solve the system by graphing. And so I'm pointing out this is not the only way that we'll be able to solve these systems, and it is my least favorite way of solving systems. These conveniently happen to be in slope-intercept form, but if they weren't, I want to point out you guys already know how to do that, right? You could solve for y, and then you'd be able to find your m and your b. So let's find the m's for these lines. What's the m for the first line? Yeah, a half. What's the m for the second line? Yeah, -3 halves. Down 3 over 2 is what that'll be when I'm thinking about it, rise over 1. What's the y-intercept for the first line? What's the y-intercept? The b, 3. And what's the y-intercept for the second line? -5. So let's graph our first line. So we'll start at the beginning at 3. I mean, that's one good thing. You guys are definitely going to get a lot of practice with graphing. Let's see. So starting at 3, my slope is 1/2. So that means I go up 1 and over 2, up 1 and over 2, up 1 and over 2. Yeah, I got plenty of points there. Let's make this a blue line. So I'll even label my line with blue here. You guys, maybe you're missing some of the colors. If you wanted to do your homework in more color tonight, feel free. I'm a fan of making the math a little bit more beautiful. You are so beautiful. Lovely math. Look at that line. I love it. Let's graph the other one. Let me start with the red. Beginning. So B is at -5. So starting at the origin, down 5. 1, 2, 3, 4, 5 for the B. And watch me move by my slope. Watch me move by my slope. Down 3 over 2. Down 3 over 2. Okay, there we go. This will be a purple line. Let's see. There we go. Get my line tool. Get some beautiful fuchsia. Happy line, really. All right, and look something like that. Draw that line. And I've got my 2 lines. First question, does there appear to be a solution? Do these lines ever cross? Yeah. It looks like they intersect right here. I think we're going to be able to find a solution. These 2 lines are going to be very happy together. They'll be able to compromise. Even though they have infinitely many solutions for each of them, I believe there will be one point where they're both going to be true. What are the coordinates of that one point? -4, 1. Lovely. -4, 1. So that's our suspected solution. All right. Now, what if it was like actually -3.9, 0.998 or so? Like it could have been. That's also possibly the case. That's where graphing is not always the most accurate way of doing this. But let's do a check just to find out. So is 1 equal to 1/2 multiplied by -4 plus 3? Oh boy. All right, so let's see. 4 divided by 2 is 2. Multiplied by 1 is still 2, and it's negative. So -2, all right, plus 3. Dealing with those fractions. Fortunately, I've got something that'll cancel out with those denominators for us. 1 is that equal to -2 plus 3? Yes. All right, but let's not get too excited now. All right, the blue line, he's happy with his solution, but I don't know about that purple line. We'll find out. Okay, all right, let's plug this in for x and y in the purple line. All right, I didn't label my purple line there. Okay, y equals, so 1 is 1 equal to -3/2 multiplied by x, which is -4, minus 5. Whew. All right, let's deal with those 2 negatives first. Negative times a negative. It's going to be what? Negative times a negative. You guys are still writing. I know I could. Sorry, I write so fast on this. Negative times a negative is a positive. All right. So this is going to be positive. 1 equals some positive number. 4 divided by 2 is 2. And 2 multiplied by 3 is 6. Oh, there it is. There it is. Look at that. 1 equals 1. It's a beautiful day, my friends. It's a beautiful day. We had 2 completely different lines when we started, and we found the one point that makes them both happy. Yeah, this is a lovely, just lovely love story here. I think you'd agree, right? Beautiful story. Let's see, where's my notes? Sorry about that. Yeah, sometimes when it all tabs on me, it gets all jittery in the flickers. All right. I think, yeah. Well, let's get this next one going. Let's roofing problem, example 3. We'll see how far we can get. We'll at least set up the 2 equations, because that's the tough part, is writing some of these equations from word problems. All right. I mean, in terms of process, it's not that bad. I mean, it's not the most fun graphing stuff, but I mean, like, it's not that difficult. It's just a combination of a bunch of the skills you already know how to do, which is kind of how boss fights work, right? In a video game, like, they have you fight a bunch of little minions with all sorts of different abilities, and then the boss fight suddenly comes in and it's like, wow, I got to use all my skills simultaneously to solve this problem. This is great. All right, a roofing contractor buys 30 bundles of shingles and 4 rolls of roofing paper for $1,040. Okay, in a second purchase at the same prices, the contractor buys 8 bundles of shingles. Find the price per bundle. Let's see. For $256, my bad. All right, find the price per bundle of shingles at the price per roll and the price per roll of roofing paper. So I've got 2 equations here. All right. Let's first figure out our x and y. Now, the x and y are likely going to be the question that they ask. All right? So my x, defining my variables, is the price for shingles measured in dollars, and the y is going to be the price of roofing paper. I actually paid a guy to re-shingle my shed just last month. Great. I'm very pleased. So I defined my variables. Let's write our equations now. So let's see. My first equation, when you bought 30 bundles of shingles, so we'll call that 30, and I multiply that by the price of shingles, 30 times x, plus 4 rolls of roofing paper, plus 4 times the price of roofing paper is y. It cost $1,040 equals 1040. Yeah. And let's see. So that's our first equation. Our second equation, he said when he bought 8 bundles of shingles. Let's see. So 8 bundles of shingles. Shingles was x. So 8x. It seems as though the second purchase, they didn't buy any of the roofing paper. So plus 0y, or I could just leave that blank, was equal to $256. So there are my 2 equations. Now, when I have 2 equations, all right, and 2 unknowns, I'm looking for both x and y, right? If you have 2 unknowns, you're going to need 2 facts to help solve that riddle, and that's exactly what we're doing here. We'll graph this electronically so you guys can follow along. But what you would typically do is you would have converted those into slope-intercept form and graphed them. You also feel free to use Desmos calculator to do some of your graphing tonight. I even included the link on your homework. 30x plus 4y equals 1040. So let's see how far I can get. 30x plus 4y equals, nope, deleting things. 4y equals 1040. So our first line doesn't even show up on the grid, and then 8x equals 256. 8x equals 256. All right, so I can't see either of those lines right now. Let me zoom out a ways. Oh, there's one. And the t'other? Where's the other line? Can it? It should be a vertical line. Oh, can it not do vertical lines? X equals 32 is the equation. Oh, dear. Oh, what if I want you to graph that? Oh, that's too bad. Let's see. Let me change the scale on this. Y-axis. No. Let's see. So basically, I've got to figure out when is this equal to 32 for x. So my intersection would occur right about here. Ooh, let me grab a screenshot of that. I nailed it. But I would graph them. The reason the other one didn't show up, I guess it's a function grapher. It didn't graph a vertical line. And the vertical line would have been at x equals 32. All right. If I divided both sides by that there. but our solution looks like it would have been at $32.20, meaning the price for shingles is $32. The price for roofing paper is $20. Let's see, I'm going to cut it there. Thanks for watching, Internet friends. Have a great day.